Hi, this is an introductory video to inorganic chemistry and where elements came from, and a bit of a review on quantum mechanics. So since we are starting our course, let's start at the beginning and talk about where the elements came from. So based on the fact that our universe is expanding, we have a theory called the Big Bang Theory. And this says that 15 billion years ago, the universe began as pure energy. And in the very, very beginning, there was no matter. It was just pure energy. And everything was very hot. So about 2 hours after the Big Bang happened, everything was expanding. And this expansion allowed cooling to happen. So during this cooling process, particles formed, and these are where the subatomic particles we know as protons and neutrons. Those ended up forming nuclei, and the nuclei then were attracted to another type of particle called the electrons, and we got some light atoms like hydrogen. Gravity formed, and then we got stars, and in stars we got fusion, which allowed formation of heavier elements from those lighter elements. And so all of the elements that we talk about in this semester are metals, and you can keep in mind that all heavy atoms and those metals were formed in stars by fusion. And in fact, if you have any metal jewelry on right now, it's neat to think about the fact that those metal atoms that you're wearing were formed by stars. Okay, so let's talk about a brief history of our understanding of atoms, and we're going to start with hydrogen atom. During this discussion, it's useful to remember that the electrons in atoms have both wave and particle-like properties. And so we're not just talking about particles when we're talking about electrons, but we're talking about something that has a dual nature. But we didn't understand that in the very beginning. And the first real observation that we had on the structure of a hydrogen atom was the line spectra that come when you burn hydrogen. And so here is what you would see for line spectra. And it was in 1888 that Johannes Rydberg first explained these line spectra, or at least he couldn't explain them, but he fit them to a formula. And he found that this formula, it's 1 over the wavelength. So this is the emission wavelength of these lines down here. That's equal to the RH, which is the Rydberg constant. It's just a number. And that's multiplied by 1 over n1 squared minus 1 over n2 squared, and where n1 and n2 are integers. And so, they're just numbers 1, 2, 3, 4, 5, etc. And so there are regions of these line spectra throughout the spectrum. And so we have a region in the UV spectrum, and the UV spectrum is down to the very far left here. So that's your Lyman series, and that's where the N1 is equal to 1. Your Balmer series is in the visible region, and that's where the N1 equals 2. Your Paschen series and your bracket series, where N is equal to 3 and 4, are in the infrared region. So Johannes Rydberg fit this data to an equation, but no one knew why the n numbers needed to be integers, and we didn't understand what the Rydberg constant was all about. This equation was really useful, but the equation was useful for explaining the data, but it didn't really explain why. And in 1913, Niels Bohr was the first one to explain the spectral lines. Why were they based on integers? And he came up with this planetary model of the atom where electrons exist in circular orbits. So this is also called the planetary atom model. And basically, he showed that, if this is your nucleus, this red dot, and these white circles are orbits for an electron. And here I've shown one electron as a little yellow dot. So the line spectra would have occurred from the electron being excited and then falling back down between these circular orbits, which corresponded to integers. So the problem with this model was that it failed for large atoms. It worked for hydrogen, but it didn't work for anything larger than hydrogen. And it conflicted with an uncertainty principle. And so the uncertainty principle basically says that for something moving so fast as an electron, you can't know exactly where it is. And this planetary atom model indicates that you know exactly where the electron exists in a circular orbit. So these were two problems that scientists had to deal with and find a solution for. And then finally, in 1926, our modern model for understanding the hydrogen atom came forth by work of Schrödinger and Heisenberg. And this is what you might have seen before in PChem or in a physics class. And here we have the Schrödinger equation. So this is modern quantum mechanics. Now in this equation you have the Hamiltonian operator. This is just a set of instructions that tells you what to do with the function that follows it. And we have the wave function. And the wave function ends up being the solution, or basically where the electrons are going to exist. And we also have an energy term here, and I'm going to talk about that in a moment. But the solutions to this equation describe what we know as atomic orbitals, and they tell us the allowed energy levels for an electron and the allowed regions in space. So the wave function is defined by three quantum numbers, n, which you might know as the shell number, L, which you might know as the subshell type, so an S, a P, or a D, for example. And M sub L is the orientation of a particular orbital in space. And then the fourth quantum number describes the spin of an electron. And this is something, the spin of an electron is not a real thing. They behave like bar magnets, but, and we explain them, we simplify them by saying that they are going to behave like bar magnets and that they have a spin, but they don't really have spin. So that's something to keep in mind as you're going through this. This quantum mechanics stuff that we're going to talk about is a little bit too abstract for our brains to really understand well, and so it's easier to just describe it as a spin. So about that energy term, the allowed energies can be found through this equation. And so this is E of n. So n is any shell number, so any integer. And it's equal to HCr z squared over n squared. So n is your shell number, and z is your the charge of the nucleus, so a positive charge of the nucleus. You'll see this with a negative sign here. Sometimes your textbook is a little loosey-goosey with this and just drops the negative, so don't let that confuse you, especially if you're an engineer and you're used to paying close attention to that. Don't let it bother you. But it's useful to know in this case that your HCr term, this can be simplified and just you can replace that with 13.6 electron volts. And so what this means, or where you will use this, is in finding ionization energy for a hydrogen atom. So a hydrogen atom has its electron in the ground state of n equals 1, right? So the electron in a hydrogen atom has its electron in the first shell. And the Z term is also 1 because it only has one proton. So essentially, you can just say that the energy of the electron in a hydrogen atom is equal to negative HCr, or negative 13.6 electron volts. You'll also see this is just stated that the energy is 13.6 electron volts. So it's useful to know this equation because you can use it to calculate the energy of an electron in a hydrogen-like atom. And this also gives you the ionization energy of a hydrogen-like atom. It only works well for hydrogen. So you can use this equation for other atoms, but the value that you pull out is not going to represent the actual value for ionization energy. And that is because there are more complicated things in larger atoms, like there's other electrons, and those are going to play into it a little, those are going to affect the ionization energy, and we're going to talk about that when we talk about multi-electron atoms. But here we're just going to limit ourselves to one electron atom, hydrogen. Okay, so let's talk a little bit more about the Schrodinger equation. So the solutions to the Schrodinger equation define the wave function, or in other words, they define where the electron can be in space. And it's actually not the wave function that you think of when you look at orbitals, but it's the probability density, or the square of the wave function. So in this diagram here, you see that there is a purple line. So this purple line here, that corresponds to an actual wave function. So the wave function is not probability, because probability cannot be positive and negative. And so this wave function has a positive region here and a negative region here. When you square the wave function, then you get the probability density. And so that's what this is, this blue line. So you have the probability density here is a positive, and then when you square the negative value, you also get a positive. And so this would be, if this were an orbital, here you'd have the nucleus, and then you would have a high probability of finding the electron, and then no probability, and then a little bit probability here, and then you would be nearing no probability at all. And this is a figure 1.4 in your textbook for reference. So the probability of finding the electron is the probability density, not the wave function. The probability density is simply the wave function squared. The wave function can be positive or negative, but the probability density is always positive. So you can only have probabilities of positive or 0. Now, where the wave function is crossing 0, or wherever it is 0, so here's it is 0, here it is 0, and out here it's approaching 0. This is where you can have either a node or a boundary surface. So where the wave function is actually equal to 0, that means the probability density is also 0. So you can see here where the wave function is 0, when you square it, it's still 0. So this is where you have 0 probability of finding an electron, here as well, right? Where the wave function crosses the origin, or the axis here, where it's 0, you have 0 probability. This is where you'll find a node. So where the wave function is approaching 0, or where the probability density is approaching 0, this is where you're going to find a boundary surface. And so that's not a node, but it's basically where the orbital ends. So here it might be useful to talk a little bit more about nodes. So there are two types of nodes, and I'm going to write them here. So you can have a radial node. And a radial node is a spherical node. And these are going to depend only on your value of n, so your shell number. A radial node that you may be familiar with is, so for example, in an s orbital. So if I have a 1s orbital and I have a sphere here, and if I cut that sphere in half, it would still just look like a circle. But the 2s orbital actually has let's say this is a negative region in the very center and a positive region. And so between these two lobes, the negative and the positive, there's actually a node. And so this guy depends on n, and that is a spherical node or a radial node. You would know how many radial nodes you have because it's just the value n minus 1 minus L. So the second type of node that you can have are angular nodes. And these are nodes that are defined by the subshell, and these are usually planar. So they depend on L, or your angular momentum quantum number, and these are basically what are going to give your shapes. So a p orbital, for example, if you look at a 2p orbital, there are two lobes here, and there's a planar node that goes there. If you look at a 3D orbital, let's say that we're just going to look at the one that's shaped like this, right? You actually have two planar nodes that go through this. And you can look at the diagrams in your textbook to reinforce that information. They have some nice three-dimensional images that will help you understand this. Okay. And so your radial nodes are where the radial part of the Schrodinger equation is going to equal 0, and the angular node or nodes are where the angular part of the wave function are going to equal 0. So keep that in mind during the next part of this discussion. Okay, so speaking of the radial and angular parts of the wave function, that's what we're going to talk about now. So this is the wave function, and the wave function depends on three quantum numbers, n, l, and m sub l. And it has a radial part and an angular part. So the radial part is the part that I'm showing in kind of the green color here. It's the radial variation, so it just depends on where you are or how far you are away from the nucleus. Depends on the radius. And this means that it depends on the quantum numbers n and l. So that's why you see radial, so this is the radial function depending on n and l, and that's your radius. And it's going to be multiplied by an angular variation, or the angular part of the wave function. And this depends on the angle with respect to the axes. And these are your angular coordinates. And this part of the wave function is going to depend on your angular momentum quantum number and m sub l. So here we have a diagram that shows you the r is radius, so that's what the radial dependence or the radial variation depends on, and your other two angular coordinates here are going to go into the angular variation part of the Schrodinger equation, or excuse me, part of the wave function. So as far as these equations go, you don't really need to memorize this stuff, okay? But I want you to look at it and be able to understand what it means. So this is table 1.2 from your Shriver and Atkins textbook, and it shows the radial wave functions for a hydrogenic orbitals. And so you can see, just like I said, the radial wave functions are going to depend on n and l. Now here are the graphs of the radial variation of your wave function. So in the first figure, this is figure 1.9 from your textbook. This is the radial wave functions for the s orbitals, 1s, 2s, and 3s. And notice here is your 0, and these wave functions are positive and negative depending on which one you're talking about. Down here is the radial wave function for some p orbitals, and again, here's your 0, and so you can see that the wave functions have some positive and some of them have negative values. So again, this just depends on how far you are away from the nucleus. Here's the probability function. So now we're talking about squaring that r value. And so we're squaring, the whole r. They represent this as r squared. Just when you see that, just think of this. It's analogous to the probability. So the yellow line here is for 2s, and it actually corresponds to the pink line up here. So you can see that the 2s wave function had some positive and negative values, but the 2s radial distribution function, or the probability function, has only positive values. And then down here, you can compare both of the green lines are the same. This is just the wave function, and here you have the radial distribution, or the probability, where you're going to find that electron. So these are images from a different textbook, and again, here are your radial wave functions. So these are going to have some positive and negative values, and then here the values are squared. So this is for your 1s here for radial wave function, and 1s down here for your probability or your radial distribution. And the 2s up here is the wave function, and the 2s down here is the radial distribution function. So take a moment and look at these and make sure that you understand how you would get this from this qualitatively. I'm not asking you to do any mathematical manipulations at this point. All right, so now let's talk about the angular variation. So if you compare the last table I showed you to this table, you'll notice that the angular wave function depends on these angular coordinates here. And you'll see a lot of these angular coordinates in this guy, or in these equations here. And just like we said before, this part of the wave function is going to depend on L and M sub L. And your book does not go much into the angular wave function. There's a better explanation for this in Miesler and Tar. But in short, it just gives you the shapes of your orbitals. So here are the shapes that you'll find in your Shriver and Atkins textbook. So you have your s orbital here. You can see wherever you are in space, at any angle, you'll be in the same type of shape. Here, if you're along the z-axis, it looks a lot different than if you're on the y or x-axis. So these have angular variation. Same thing here. Here you have some angular variation. These images also show you the nodes. These are all planar nodes, even the ones that look like a cone, like this one here. This is technically a conical node, but it fits into the same category as the planar nodes. So we have some planar nodes in the p orbitals and some planar nodes in the d orbitals. So let's look at one of the tables from the Miesler and Tar textbook. So this is for the angular variation. And I just want to point out that these angular coordinates are hard to show. So we have the L and the M sub L. This coordinate here is actually really hard to imagine. And it's hard to imagine because it isn't real. So if you look very closely at these numbers here, you'll see I, which is an imaginary number. So you can't really begin to understand what that might look like unless you can think in imaginary numbers. I can't. But you can almost imagine what the square of the waveform of these kind of things would look like. But don't worry too much about it. Just understand that these are imaginary numbers. So it takes mathematical manipulations in order to transfer them into real wave functions. So over here we have our angular factors, and over on the other side we have our real wave functions. And so this is where mathematical manipulations have converted the imaginary functions into the real functions. And here you can see the three-dimensional boundary surfaces for the simplest examples of s, p, and d orbitals. So really what I want you to understand here is that the angular variation is different than the radial variation, and you don't get the orbital unless you put them both together. All right, well, the next video is going to talk about many electron atoms, so I will see you then.